So for our processing technique was delays. I'm Monica Wolski.
And I'm Michael Wood.
All right, so basically delays. So delay is a method used in sound processing. It is the time difference between two identical sound samples that are playing at a set or different interval period. So this means basically you have one sound and then you can either delay the sound by like 10 milliseconds or even up to 10 seconds, and then it repeats the same sound. Some early use of delays. So effects were achieved by reel-to-reel magnetic tape recordings. So this is before the cassette. So reel-to-reel are basically like little machines that has one reel and it just takes over the tape to the other reel. So it was very kind of limiting with what you could do with the delay effects. This was actually a common technique used by early music composers. Later on, tape recorders were used for the analog delay effects. And the first digital delay effects started between like the 1970s and 1980s. The tape recorders became like mainstream around the 1950s, so more composers and artists could actually use this in order to manipulate the tape and create a delay effect. Some examples of early composers. Pauline Oliveros used a tape looping technique, and this can be actually shown in the example, which is Bye Bye Butterfly, which she composed herself. So in that example, you can hear a lot of the reverb and a lot of delays and a lot of the same sounds kind of repeating. And Carl Stockhausen would actually play back real-time recordings, and he would do this using the tape recording technique as well. So some delay effects are flanging, reverb, coarse, pitch shifting, echo, phasing, and multitap, which are some of the effects that you got to hear in Bye Bye Butterfly. So the effects that we focused on were mainly flanging, or two identical signals, only gradually delaying one. Phasing, which splits an audio signal into two. Delay lines can actually create like a variety of notches and peaks in an audio signal. So chorus, so audio signal mixed with pitch modulated copies, pitch shift, altering the pitch of an audio signal, reverb, which is the persistence of a sound, and then time stretch. So here are some examples of the main effects. So in the flanging one, you got to hear the first was the original tone, then the second one was a little bit of flanging, and then the third one was multiple signals with flanging. So that one was pretty similar as the flanging, the three different phases of it. last one was pitch shift, which was an example of like an electric guitar. So being the first was the original chord, and then the next one was pitch shifted using delay techniques. And now on to the next patches.
All right. So I guess we'll just try to break it up for each effect. So I guess we can start with the chorus effect, which basically what it's doing is it's taking in two signals. One of those signals is being modulated by a random number between a given amount. So what the rand object does is it's kind of like white noise, except more discrete, I guess. It's less values happening less often. So what that does is it basically the unmodulated signal passes through, and the modulated signal gets sent out through here and sent back in. So what it's doing is it's basically sending one through and delaying the other by the random number amount, and it's the pitch kind of gives it this effect that there's more than one voice, which is what the chorus effect is supposed to achieve, is to make it sound like more like a live performance, less perfect and more, I guess, out of tune-ish. So we can go ahead and move on to the next one. This is the echo effect. So what this is doing is it's basically sending a signal into the delay object and then amplifying it by a given amplitude, which in this case is 0.85, and then passing it back into the delay to be sent around and around until that reaches near absolute zero. So what that kind of does is it makes copies of the sound that play back and have less amplitude each time it passes through, which is a pretty basic concept. For the flanging, we have one signal that's being split in two. One of them is being just sent straight through, while the other one is being delayed. And what this is doing is the cycle object, it's a low frequency oscillator that's modulating the amplitude and pitch of the modulated signal, which is then being added back in. And what that kind of does is it makes that phasing difference and that kind of difference in pitch, so that when you hear the two together, you get that flange effect. And for the pitch shift, this one is a little bit confusing. What it's doing is it's kind of using the same principle as like the Doppler effect in order to raise the pitch of a given signal without actually affecting the frequency. So what it's doing is it's sending the signal into these two cosine ramps, which is basically just some math to basically equal it out, because the way that you create the general effect is you can take a phasor object and combine that with the actual signal, and that'll kind of make this shifting of the pitch, but you'll get really harsh popping and clicking. So what the cosine ramp will do is it'll offset the phase and normalize it between two values, so you don't get as much wavering as if you would with a normal cosine ramp. So by sending it back and forth between these two separate cosine ramps, it kind of creates this effect of raising or lowering the pitch. And lastly, the time stretch effect, which is a little bit odd as well. What it's doing is it's using the delay object, and over the course of 130 or 13 seconds, it's raising the delay in samples from 0 to 10,000. And what that's doing is it's basically stretching out the buffer that the signal is coming through. So you're delaying it by 0 samples, but then you kind of raise that over time, but Max has to process through the buffer as it would normally. So what it kind of does is it has this time stretching effect where it basically stretches out the sound and slows down the sound without actually affecting the pitch. And lastly, to combine all these effects, we made use of some audio routing using the matrix object. So basically the way we have it set up is that you can route any audio to any output, so any input to any output. So we have all the inputs up here. So you have just unmodified, the flange, echo, whatever they happen to be, and then they can be routed to any output. So you could take the unmodified and pass it to the echo, and then pass the echo to the flange, and then you can even make them run all in parallel. It's kind of really open to do whatever you want. So the way it works is basically the matrix object has all of its inputs, so left, right, flange, pitch shift, and so on. and then it's 7 outputs. And what these two, this is actually sending it to the left and right channel for output, and then these are sending it back in to the given matrix to be passed to whichever other effect. Okay. So I guess now we can actually demonstrate the patch for the last couple of minutes.
Is it still recording?
Yeah, it should be. Ooh. This is quite a mess. Oh goodness. Why is this window so big? Oh,
The green.
oh that makes sense. Okay. So I guess to start, we can just kind of show how the routing works. So you'll see that we have channel 1 being sent to channel 1 and channel 2 being sent to channel 2. And that's basically saying to send the left channel as an input to the left channel as an output, and then to send the right channel as an input to the right channel as an output so that it'll pass through. Alright, which for whatever reason, the left channel is not working. That's really weird. But anyways, let's... Yeah, but it should still... Yeah, it worked on those. That's odd. Okay. So, no, now it's working. For each of the effects, we have a preset for them. So for the first one, we have the flange effect. So if you just want to like sustain a note or do whatever. So it's kind of, you can hear it like, well, not slowly in that case, but it's actually changing the pitch of the second one. Next we have the pitch shift, which is set to lower the frequency, or raise the frequency actually. So if you speak into it,
Hello.
it actually is raising the frequency by using that Doppler effect type thing. Then we have an echo effect, which is just basic echo. We have the time stretch, which if you speak into it real quick,
Hello.
what that's doing is it's just stretching out the samples in the delay, which kind of creates the time stretch effect. And lastly, the last effect we have is the chorus effect, which that's really odd. I think that might be from the feedback, or the settings are just a little too high on that. Try now.
Hello. Better.
I think it might be the depth as well.
How about now?
That's better. So then we have that chorus effect. And we actually started combining some of them, and just because we're low on time, I'll cut to some of the ones that I thought were a little more interesting. I think that it was. Maybe it was this one.
Hello.
Yeah, this one is what it's doing is it's sending it to the echo effect, which is then being sent to the flange effect. So what it kind of does, it's kind of creating this infinite feedback, and it actually on its own starts to create kind of an interesting sound, in my opinion, which eventually starts to feedback a lot. But you could use this, as you'll notice, it kind of creates almost a beat out of what you're listening to. So you could use this artistically to create kind of an improv beat. And I'm going to clear that buffer. Yeah. What was another one we had?
Oh, this one. It's more.
Yeah, so what this one's doing is it's sending the signal to the echo, which is then being sent, feedback, which is then being sent to the time stretch so you can actually control it. And then that is being sent to the flange effects. But I guess really it's whatever you would want to combine. You can combine these in any way just because of the flexible interface that you've designed. So I guess that's really all we have to show. Questions or comments?
Okay, so this is our presentation on filters for everyone. So just some just some basic stuff on what is a filter. It's an object that operates on a signal, most commonly boosting or attenuating regions of frequencies on your basic sound spectrum. And how I like to put it, the easiest way to characterize a filter is by plotting your amplitude versus frequency response curve. And that really allows you to view characteristics of your filter. Some more stuff. And then these are some images of some different types of filters that originally came from a biquad, but here's a bandpass and a bandstop. So really the major difference is the amplitude difference, how one peaks and one's a valley. So that's really, in a basic sense, how filters are made about, just basically attenuating your different peaks and valleys. And this is a cone filter, which is what we mostly use for our max patch. So it's constructed from a series of band passes in regular order through addition of a delay line, causing destructive and constructive interference. And basically it's called a cone filter because when you have the lot, it just creates all these peaks as a cone tooth would be. And then we have some all-pass filters that are constructed from a series of feed-forward and feedback cone filters when the coefficients are the same. So it's basically equal gain but phase changing. And then a few historical points. Before all the computer filtering, we did have filtering in the analog world. And one popular example I like is Alvin Lucier's "I'm Sitting in a Room." So from what I remember from Audio Fundamentals in Art is he basically sits in a room with a microphone and a speaker, and he records himself saying a certain sentence, "I'm sitting in a room," and a few other words like that escape me, but he says it and it plays through the speaker, and then he records that coming out the speaker and just basically keeps on doing that, and it kind of washes out his signal until it's pretty much inaudible. So well, I would love to spend a large part of our presentation listening to it. It's about 45 minutes, so we'll play a little bit of the beginning, middle, and end, just so you got a pretty good sense of what's happening.
I am sitting in a room different from the one you are in now. I am recording.
Go a little more back. Go like around here or something. So just to show you.
Is destroyed. What you will hear then are the natural, resonant frequencies of the room, articulated by speech.
Okay, yeah. So basically, when he records the recording and just keeps on doing it, it kind of washes out with all the reverb of it playing in the room until it's just like pretty much like white noise almost at a certain point, or it's just a bunch of like washed out sounds at the end of it. So yeah, way back in the 70s, a filter was a whole other piece of hardware instead of just a little software plugin that we used today, and they will come in 2 points or types, either passive or active, and the active will need a power source. All filters were subjective the waveform to an insertion loss, reducing the original signal, regardless of how they were supposed to impact the frequency response. And there's a whole bunch of types of filters. Like we had comb, all pass, slow pass, high pass. So now in today's world, it's not a whole piece of hardware. Like I said, it's just pretty much a button on some programs that you press now. It's all digital and stuff. So the filter that we use most was the cone filter, and it looked like I showed you before, all the low peaks of the cones on the spectrogram and whatnot. So yeah, take it over.
Alright. So cone filters come in 2 varieties. There's a type that they all have a delay line, and you can either feed back the signal or feed forward the original signal by a certain delay. And what that does, it causes destructive or constructive interference in the sound, resulting in the extreme peaks and depressions that you'd see in the amplitude versus frequency graph right there. It's very similar. You can kind of construct a fake comb filter that doesn't exactly have the phasing effect by including a bunch of band stops or band passes in a closed series of biquad filters. But then I just hear the two, this is really basically down to earth what a comb filter is. The one on the far left is the feedback, and you can see that you have the plus is where the signals are combined, so you have it passes through, then it goes, takes a delay in a certain amount of samples, and then there's a coefficient of the feedback which determines the strength of it, and it's fed back into itself, and you get the resulting sound. It's much easier to hear a feedback response in a comb filter than it is the feed forward. So we'll focus mainly on the feedback. Now, comb filtering is also an acoustic phenomenon that we should probably be able to hear in this room. The normal situation where you'd hear this more is either in an alleyway or a tunnel that has hard reflective surfaces and is usually in a fairly contained space, but if we're quiet and we make a sudden impulse, we might hear. Did you hear how it's kind of, you hear the da-da-da-da-da-da. That's, the sound waves are going out, obviously, in every single direction, and what's happening is they bounce off of the walls, some of them get absorbed into the carpet, but they come back, and then when they recontact themselves, they create destructive interference and also some constructive interference. So I had an example of comb filtering that apparently the link didn't go through correctly, but basically in studios people have to worry about getting unwanted comb filtering effects from their speakers, not only because they might be in the same phase and destroy the signals, but also if we were to take a white sound source, stream it through this signal, take the microphone, put it up there, record it, play the two back, and then move a object, a wall of some type, and put it to the side, you'll actually be able to hear the white noise basically modulate. It won't sound perfectly evenly pitched anymore. I mean, I think it's better. It's worth going and putting this into YouTube because I can't accurately describe it.
Let me tell you a story about a book that keeps getting better.
Ads are in everything.
Born
So, comb filtering can be used practically, but it's also something to be avoided in some cases. And then finally, what we focused on in our max patch is on pitched comb filters. Every comb filter has a natural harmonic frequency that will resonate on, and it's based on the formula right there. So when it gets to the max patch, I made a patch that allows me to do the math, rearranged the formula so I can type in frequency and it will calculate out based on the sample rate and that frequency and give me the pitch that I wanted. And one of the problems that I encountered with that in max is that you can't have delays in samples, so you need to go through and calculate it out into milliseconds. So then, getting to the actual pitch, there were Okay, so what I've got is basically a series of 12 modules that allow me to type in any independent frequency that I want to hear when a noise source goes into a microphone. So for the first one, I'll put in 220, which should be an A. I force the calculation, and then also in order to make it more organized and allow me to build chords and whatnot, I have a matrix object in there so I can activate and deactivate whichever ones as I please.
Hello.
So that's the basic dry signal because I don't have any feedback or feed forward on it. But if I type in, we'll put 0.9, an extreme example. Prevent it from doing that.
1, 2, 3, 4. 1, 2, 3. 4.
So it doesn't really matter what you do, it's always going to come out as an A. So one of the applications that people have used for comb filters like this is that you can actually make your own synthesizers out of it because it's extremely accurate as far as the frequency goes, and then I guess it's sort of a Vocaloid, and originally I was going to do something like that with our patch until I fell sick, so now I've got it. So
1, 2, 3, 4. 1.
So you can start to build chords, or you can mess it all up by putting in some random frequency like 672. Force the calculation.
1, 2, 3, 4. 1.
Of course, as the higher it goes, the more difficult it gets to hear. So eventually, what I can end up doing is either creating octaves or full scales of chromatic pitches even. So 235, 246, force calculation, force calculation, force calculation. Here we go. 1, 2, 3, 4.
1, 2, 3, 4.
So you can get some really nasty sounds out of this too. And you can even make the discrepancy in the frequency even smaller and get some really crunchy sounds out of it. So that's basically it for this max patch. Then additionally, there are a few other things you can do with the kind of the pitch filtering by the delay. So I'm going to put it on a metro of, alright, go ahead.
1, 2, 3, 4. 1, 2, 3, 4.
So what this one is doing is I've got it on a drunk function, and metronomic, so it's outputting a delay between 0 and 10 milliseconds, and then it's doing it by steps at 100 milliseconds. And feedback. So you can do it like that. You can do it on a random basis. Alright.
1, 2, 3.
Your first patch is still running in the background.
Ah, okay. And comb filters. And then I've got to get the. Okay, there you go.
1, 2, 3, 4.
And then the last one that we did experimenting with that is that you can also basically make it modulate in pitch with a cycle. So by doing this, you'll hear sustain.
1, 2, 3, 4.
And it'll go up
6,
and down,
7,
and eventually as soon as it reaches
9,
its
10,
top
11,
at
12,
2 milliseconds, it'll go back down to 10 and the
15,
pitch will fall.
16, 17, 18, 19, 20, 1, 2, 3.
So that's basically it for that.
All right, so we did our project on live sampling. I'm Chris.
Leo, they know us.
Colby. I'm doing it for the camera. Everybody doing it. This is like we did our project on live sampling. First, you gotta ask the question: what is sampling? Sampling basically is an art form of composing music of pre-recorded sounds. But what we're doing today is live sampling, which is recording. Well, we're going to record straight through the microphone and make music out of just instruments like knocking on the desk or using our voice and whatnot. Basically doing it on the fly. We put some advanced sampling techniques, looping and pitch shifting, but we're not going to use any of that today. We're just going to use straight recorded sounds from. Leo has a little guitar. And whatnot. I subsequently had some macaroni in my book bag, so we're going to use that. Clapping, voices, we're going to use everything to kind of compose a track, using the same rhythm. Yeah, that's basically what we're going to do. Go ahead.
One of the big pioneers of sampling was Humphrey Bogart, and he the idea of sampling before that really wasn't around. He took it and because of him we have hip hop sampling, electronic music, a lot of genres came from this idea. It does go back to as far as Pierre Schaeffer though, and I don't know why I'm pointing at Pierre Schaeffer in the 1940s. Let me see. I have some samples. It's easier to just show you, I guess. This guy is from the UK. He performs live sampling. He doesn't a lot of electronic musicians just trigger clips on stage. This guy actually records them and manipulates them on stage. His setup he has is huge. It's just a music video, but you can hear it. You can hear the marimbas that he was playing. There's that, and there's another video where you can actually watch someone do it. How do you go back to the...
Just minimize that.
Oh. And then what, go down here? Yeah. That's filters. That's the wrong one. No, it's not. And has anyone seen Bink Beats before? This guy, you can actually see what live sampling. This guy's really good at it. It's a song by Shlomo called Places. This guy gets it down to the T. It sounds exactly like a song. It's crazy. Explain the patch now. There we go.
Sure, can go back.
Yeah. Where you at? Dang it.
Click on the P.
Click on the P.
Oh, the P, yeah, the P right
That?
there. Yeah.
Okay. I don't know, Max.
Me too. But okay, it's fine.
Hit the side.
I'm trying.
Yeah, just do the
Oh, I have to do next slide? Come on. Alright, so I will be explaining the patch. Why it's not sure. But
I'll
first,
figure it out. Just keep talking.
yeah, first I'm gonna kind of explain the objects I used to create the sample we have. I don't know if you can see it. I can't even read it, so I'm just gonna do it from here. But yeah, so I can't see it. I'm gonna bring up the patch. I think it's easier that way. Yeah. Why is that small?
Why is it so simple?
I don't know.
So you can resize the screen with the green. The red, yellow, green button right there. Resize the screen, and then if you unlock, you can, or actually if you don't unlock, Apple minus will make it smaller, like zoom out. Apple minus and Apple plus are your zoom keys. Next.
Yeah, zoom out just so you can see the line.
Zoom out, but then they'll be too small.
Okay,
But
that should be good.
But yeah, so we are using the groove object. Or maybe I should start with the buffer object. So we have a buffer object which allows you to record a sample into the RAM. And then what you do, you just specify how long you want the buffer to be. And then that's how long you can record the actual sample. And then we have a groove object which it talks to the buffer and is responsible of doing roping. So if you want to be able to rope your sample that you just recorded, you can use the object to rope your sample. And then we have a waveform. You know, this helps us to visualize the sample we recorded. That way we can manipulate the samples, so we can choose like which part we want to play instead of trying to play the whole sample. Yeah, okay, so the record. And then I'm pretty sure you guys know the record object, right? Just record through the microphone and then send out to whatever you want. So that's a sub option. And then we have a sub page that is responsible for playing the actual selected portion of the audio. And then from there, it just sends to the speakers. So just to give you an example, what we're doing is we are recording an audio, and then it's sent to the buffer, and then the buffer saves into the RAM, and then the groove object takes whatever that we have been selected from the waveform, and then the waveform sends to the sub page, which is then plays the sample. But we also have a rhythm generator from our previous project, which is responsible for, like creating a synced rhythmic thing.
Stays on rhythm.
Just so it doesn't lose track, because we have we can record up to 6 samples, and then we want to play them at the same time. So with this rhythm generator, we can play everything at the same time in sync. And now we'll show you guys how it works. I'll kind of play around with it. Go to our GUI, turn on our audio thing. Is it the microphone now? Okay. You can start with the kick drum. Or
Yeah.
Are you ready?
Mm-hmm.
I think you're good. That's it.
Just get closer.
Do we have audio?
Yeah.
Come on. I'm not hearing anything.
Just feedback.
Oh. What? Come on. Alright, we can record. Let's record another one, I guess.
Yeah, it's true.
Sure, just plug the string. Yeah.
You ready?
Yeah. That's good. So I must have the routing is not Probably. Oh, correct. I don't know
Do you
why.
have like an older model of the patch that we use?
I hate when that happens. I actually don't know why it's not playing. Oh my god. I'll try another one.
So,
Oh, sorry. Okay, that's really good.
do you have this thing turned on?
Oh, that's why, I guess. Yeah. But still. Oh,
Yeah. Yes. Yeah.
oh.
There you go.
Oh, it doesn't select. Maybe one. Yeah. Come on. You can record something outside.
Macaroni.
Yeah.
Come on.
That's good.
Yeah.
Got like 8.
No.
Dubstep. Yeah.
Album. 16. We record that again. So. Yep. Again.
Get the last.
I don't know. But yeah, as you can see, some web is not working, but you can actually create a beat on the fly using the samples you just recorded. It doesn't have to be a beat; it could be some cool sounds.
Yeah, using rhythmatic. Play it like on the fly. It's kind of cool. Yeah.